Okay. You are on YouTube now. Okay, it's full screen now.
Let's go. So I'll talk about now about the implementation of the sediment into CROCO and how to use it. So the SPPK, the input files, and so on. So about the implementation, it's basically the same presentation than before, but translated into models terms. I will come back on all this notion of settling velocities, bed load, transport load, and so on. So for this presentation, I will talk a little about the equations. So some stuff you may have seen with Swain yesterday about wave current interaction. Just I will recall the equation by using. Some words about the bottom boundary layer. So the fact that for the sediment, you need to compute a kind of a skin friction, which is not the same that the one you use for hydrodynamics. And then I will have some words about the equation for the sediment itself, the cost structure, I think very briefly, and the model option. And I have also some examples of what can be done at a different scale. So about ocean dynamics and sediments, so it's the same, as you see, the same thing than before. So here in this talk, I will address the sediment model, but also computation of this bottom boundary layer, the way it interacts with ocean circulation and the way it interacts with waves. So it's a presentation which is a bit more oriented toward sediment transport in a sandy environment, a bit more than estuaries environment. So as I said, what matters here is that you need some wave data or wave model to be able to model those sediment properly, at least in nearshore environment, but even for estuaries, I think. So the wave average equation. So I think Swen explained this yesterday before. Do it better than me. So you consider equation if you want to take into account the wave influence on your circulation. Sorry. You need to consider if you want to consider the influence of the wave on your equations, you will have additional terms appearing in your primitive equation. So here in this set of equations, on the left, you have the traditional primitive equation, and on the right, the effect of waves. So you can see for the momentum, for instance, you got a term which corresponds to the interaction of the stocks, velocities, and the velocity. That for the tracer, you got the transport of tracers by the current and the standard current velocities, but also a transport of tracers, so of sediment, by the stocks velocity. And what happened here, well, here in the scheme, it's a kind of scheme I also showed before. So when you have wave, you got orbital velocity of the waves, which are reaching the bottom, and then some additional friction at the bottom, leading to erosion of sediment. And you got also additional phenomenon like breaking, which will change the mixing, the vertical mixing in your configuration. So about the bottom boundary layer, as I said, the bottom roughness is one of the main drivers for erosion, for sediment modeling. So it matters for erosion and rust suspension for sediment in general, and for non-cohesive sediment, it matters for bedload transport. So bedload transport, it may not be, as I said, super intuitive, but it's what happened very, very near the bed. So in this area where you're not exactly in the water column, but you're not exactly in the bed either, you have a kind of the area where you have a kind of mixtures between water and sediment. Or another way to see it, if you imagine a gravel into a river, so the gravel are moving because they are rolling on the bed, they are not in the water column. And the same happen at a different scale for the sand. And in the other way around, having sediment will change the rugosity of the bottom. So if you consider the classical formulation you have for the ocean, for instance, you may have saw last week or this week in the CROCO options that you can have, for instance, bilinear stress, so here, or you can have also a logarithmic stress, so you compute which will depend of a typical roughness length. And for if you have sediment, you have to consider this rugosity based on a Solby formula, which take into account the current stress and the wave stress. So this is for the sediment, and on the other way for the current, the stress will now depend on the sediment characteristics, so on the sediment rugosity. And if you remember in your CROCO.in file, in the bottom stress section, you got a parameters which is called ZOB. So without sediment is something which is fixed. So it's something like 0.1, 0.01, which is a typical rugosity length. And if you have sediment, your ocean will see the rugosity of the sediment. So as I said, we have two models into CROCO, so USGS model and an Ifremer model. So I will talk about the USGS model, but basically what is done in the Ifremer model, it's more or less the same. And I know maybe Guillaume will present some test cases with the Mustang model. And what I will present, I think it works also for other sediment models. So, as I said, those models, they can do both cohesive and non-cohesive sediment. But with the USGS model, we are more experienced with non-cohesive sediment, and some people are more experienced with cohesive sediment. And there are some developments underway in both models, so both models are alive. And both models are also documented, and we have test cases for both models. So for all test cases with sediment, you can choose to activate either USGS or Mustang, and you can compare the results if you want. So what is done in CROCO, especially in USGS? So we deal with sediment transport in the water column. We deal with erosion and deposition of sediment at the bed level. We can deal with the bedload transport, so transporting sediment in contact with the bed. And in addition, we compute also the bed evolution. So with a standard configuration of CROCO without sediment, you got a certain number of layers inside the ocean. And with sediment, you have a number of layers also into the bed. And in each layer, you will give the composition of this layer in terms of sediment and of percentile of sediment. And you can also use morphological evolution. You can also neglect it. So in terms of implementation, so the sediments, they are considered as dissolved in the water column, and they are treated as any other tracer, passive or active tracer in the water column. So the change rate in time will be due to the transport, to the mixing, with additional source and sink terms. So a sink term, which will be the settling of the sediment in the bed. So the water column here will lose sediment through settling, and there will be an input of sediment through the erosion. So you will have in the model, you can deal with multiple sediment classes. It's you have to define how many sediments you want to define, and for each sediment, you will have to input a certain number of properties.
100, 1200 de Francia.
Y de México.
Como 700.
300 de México y 1000.
Más o menos. Sí.
Pues está bien.
Sí, más o menos. Pero porque, pero cuando estoy en México solo recibo el de México.
Sí. Bueno, yo no soy Cotipela.
Tú eres beca 100%.
IRB.
Pero no puedo quedar.
No puedo quedar en México cuando estoy.
Excuse me, I'm hearing someone speaking.
Fue que modificó esto, porque antes estudiar el doctorado te costaba menos de 100 euros al año.
Sí.
Ahora puedes estudiar. Por tema de impuestos, no puedo estar más de doctorado. Si hubiese mantenido las mismas tasas, sería.
So you can so you will define, you will have this equation for the sediment, and this equation resolve as for each type of sediment from 1 to whatever number you want. And for all sediments, you will have to define the grain size, the density, settling velocity, and some value, some critical rate for erosion and deposition. And basically, all of these values are related to the grain size, meaning you got some formula to compute settling velocity. I mean, it's pretty obvious, intuitive, will depend on the grain size. So you have this equation, which is not the shown equation. So with additional sinking and source term, you have standard boundary condition like for ocean, and for passive tracers. So for this sink term, the velocity, the settling velocity will be a constant for each kind of sediment, and will depend on the class of the sediment, so of the diameter of the sediment. So for the source of sediment in the water column, it's an erosion flux, an erosion flux. So some sediment is taken from the bed to be put into the water column, and this term of erosion will also depend of the sediment size, because basically it means that a sediment which is a very light sediment, like mud and clay, will be easier to put in motion than a sediment which is heavy, like sand. So you have an erosion which depends on critical shear stress, which is characteristic of the size of the sediment. So this critical shear stress will be a parameter that you will have to input to the model. And for the mixed or cohesive case, you will have also you will also compute some consolidation capabilities for the sediments. It means that this critical shear stress will evolve in time. So as the critical, it will be more and more difficult to erode sediment after some time, because this sediment will be more and more compact. And so this is for erosion deposition and transport in the water column. But for the bed load, so bed load, this is what happened very near the bottom. where sediment is put in motion, but without being in the water column. So it's not resolved explicitly because, of course, this happens at the scale of the sediment grain, but it's a flux which is in both directions, for which we have a different parameterization. And we compute a flux of sediment, which also depends on the grain density and a critical stress in both directions. And we also be able to take account the effect of slope, so avalanching of sediment when the slope is too steep. And here again, this is also a parameterization depending on the angle of the topography. So we have different formulation for bed load. First one is called the Meyer-Peter formulation. This is one which it's a pretty old formula, actually, which was developed originally with river. So it's more suitable for rivers, continental shelves. And you can see that this formula does not take into account waves. So basically, this here the computation of bed load depends only of a skin friction, which depends on the current. And then you have also another formulation which will take into account the asymmetry of the waves, and which is one which will be much more suitable for sandy environment and modeling of beaches, because the transport of sediment, as we saw, will be asymmetric. The bed load will be asymmetric between the crest and the throw of a wave. And in terms of morphodynamics, so as we saw, there will be erosion of deposition of sediment, so the bathymetry will change in time. So this doesn't mean that we need necessarily to use morphodynamics. We can decide that this evolution of bathymetry is very small, and at the end we want just to neglect it. For instance, if we do a sediment at, I would say, an open ocean, we don't need to use morphodynamics because bathymetry will change very little. But that if we are near shore, we need. So we compute the divergence of the sediment fluxes, and we compute variation rate of bathymetry. And we have to, and then there's modification of the vertical velocity at the bottom. We have a vertical velocity at the bottom to take into account this variation of bathymetry. So it basically what happens here, we have the original bathymetry, we have wave and currents. Then we're able to compute sediment transport. From the sediment transport, we are able to compute erosion and deposition, then bed evolution, and then here again. So here an example of what was done. I think it is in the test cases available. So it's a flume experiment, so a totally controlled experiment, and where we start from a planar beach. There is a forcing by wave. We generate wave in a channel. There is a planar beach. And then there will be the formation of a sandbar. And you can see here the differences between the model and the flume and the observation. And it's pretty cool. We're able to form a sandbar, which is here, and to erode here. And what happens here physically is that we got some erosion in this area. Then so the sediment which is eroded here is put into the water column, is transported here into a convergence area where the residual velocity are weak enough to allow the sediment to sink and to deposit here. And in terms of bed models, so as I said, one difference with sediments that in addition to our ocean model, we also have sediment layers under the ocean layers. So you will have to define a certain number of layers and keep in mind that it has a cost. So basically, you don't necessarily want to use 50 layers of sediment because you will have to compute everything. And so you will tend to erode for instance, the first layer of sediment. So here you have the ocean, here the bottom friction. You will erode the first layer, and once you have eroded all the layer, you will form a new layer of sediment. And same goes for the deposition. There will be some deposition of sediment, and if you have enough deposition, you will have here a new layer of sediment, which will be formed by this deposition of sediment. And in terms of code structure, I'm not sure you will go into this, but basically the way it is done is just we have one routine for each term we are computing. So all what is initialization and input data are done the same way than for hydrodynamics. So it's at the beginning of the computation. And we compute the hydrodynamic fields, so barotropic fields, baroclinic fields. Some we compute also a mixing. And then, as it is for the biology, we compute the sediment. So for what I mean by computing the sediment is computing all the different terms. So the erosion, deposition, transport through bed load, and the redistribution of sediment in the bed. And here it's what we have. So we have this main routine for sediment. Then we compute the different fluxes happening. So the flux through a bed load, the settling of sediment, the erosion of deposition of sediment, and then we update the bed properties, and eventually we apply the morphodynamic. And if I go a bit more into the details, so it's basically what I said before, just a bit different. So to compute the bed load, we need to compute the bed stress, so a composition between the current shear and the wave shear. Then we will compute the transport through bed load using one of the two parameterization I show. Eventually, we will have the effect of slope, and then we will compute the fluxes of sediment near the bottom. And same goes for the settling. So we have this vertical settling velocity of the sediment as an input, and we will update the concentration of sediment in the water column through the computation of transport through settling. And same goes for the update of bed stresses. Once we know the fluxes of sediment, we can update the first layer of sediment, so the layer which is in contact with water, and which will be updated with an amount of with an input of sediment if we have deposition, or loss of sediment if we have erosion. And then we have the computation of all the layer of the bed structure. So all the layer, the composite base, it's basically the composition of the bed layers. So the percentile of each type of sediment in the different layers. And in terms of options, so Guillaume will come more about this. So you have the first set of options which are related to the computation of this skin friction. So it basically, you're not forced to do it, but I strongly advise to do it. If you use sediment, you want to compute this particular stress, taking into account the wave influence. So this is this key BBL in pp.f, it's ppdef.h. So it means that you will compute this bottom boundary layer and this specific trace to be taken, to be used into sediment. And then you need to have one option for the wave. So either you have wave data, either you will move some, you will use some analytic values for a wave. And then if you go really into sediment, so some sediment parameters are hard-coded. So you have the number of layers of sediment, and you have the number of sediment classes. And this is in a param.h, like the one you use to define, for instance, the dimension of your domain. What you can see here, for instance, for different configuration. So here it needs, for instance, if we take this one, it means that we have only one kind of sediment, which is non-cohesive, and we have 11 layers inside the bed. Or if we take this one, for instance, we have 4 types of non-cohesive sediments, 15 cohesive sediment, and 20 layer of sediment inside the bed. And we have also a number of gravel sediment, but it's not functional. So you have to define either a number of sand, so what we call sand is non-cohesive sediment, a number of cohesive sediment that we call mud. It's kind of well, a shortcut. And then once you have defined those parameters in param.h, you got some keys for sediment. So here again, Guillaume will come back on this for the test cases. So you have to define if you want to use USGS model, which is the key sediment, or Mustang model, which is, or Ifremer model, which is key Mustang. And then you have to choose if you want to use suspended load, so transport over in column, or bed load, or the two. So usually you will use at least the transport the water column and eventually some bed load. And then you've got a lot of different options corresponding to the different parameterization for bed load, for instance, corresponding to the morphodynamics, kind of different stuff. But for this, I would say that the default choice, I would advise to stick to the default choice. And so to sediment, you have first to define DBL, to change param.h, to define some keys in cppdev.h, and then you've got a specific input file, text input file for sediment, which is called sediment.in. So here again, you will see it with Guillaume. But in this, you will define the diameter of each class of sediment, the initial concentration in the water column, the density of the sediment, the settling velocities, and the erosion rate, the critical stress, and the fraction of sediment in each layer for each sediment. So you have as many lines here as you have a number of sediment. And then for each bed layer, you have to define the thickness of the bed layer, porosity of the bed layers, and then other values that we don't change a lot. So some example about this. So here it's some modeling in Vietnam. So here you have Hanoi, here you have Ho Chi Minh City. And the question here was the question of the erosion of the Mekong Delta. But there is a lot of concern because there is the feeling, Vietnam, there was a feeling that the delta of Mekong is eroding, and that it is due to a decrease of the supply of sediment through the Mekong here, because there are a lot of dams which are built, a lot of dredge, and human exploitation of sediment. So it's a modeling we did, and we compared to satellite observation, and we can see here that the input of sediment here is transported around all along the coast here with a rock deposition at the end of the peninsula. And another example was still in Vietnam. It was at near shore. So it was here. There is a river actually at this point, and there is an erosion which is due to waves. So you got oblique waves, some erosion there, and a deposition at this point. And if we compare with some data, I think we are able to compute the correct migration of this part here. And another example is in Senegal, in Saint-Louis. So here you have this in Dakar, sorry. So here you have the city of Dakar. Here you have the open ocean, and here you have a very, very long sandbar, maybe something like 40 kilometers long and 200 meters wide, which is protecting the city from the ocean and which is eroding. So we use, and the question is the erosion of this sand barrier. So we use the model to simulate what would happen if we put some breakwaters somewhere else. And what we can see here, that if you put so here you have your original domain. If we put a zoom somewhere here, you put some breakwaters at this point, and you are able to limit erosion and to accumulate sediment at this point. Because here the wave will be broken, and you will limit the erosion at this area. And finally, one is an example which I think it's also in the test case. So it's a flume in Netherlands, which is almost something which is almost something of a real dimension. I think it's 200 meters long. It's a flume which is 200 meters long, and we use it to simulate the migration of sandbar. So we have with a different scenario, and the difference of the scenario is the difference of wave amplitude. So for the first one, we have very energetic waves, so one meter waves, and we are able to have the original bathymetry there, and in the dot line, and we're able to create a sandbar and to have the good proper migration of the sandbar offshore. And here with for the second scenario with a smaller wave, we have the migration of the sandbar onward, and we're able also to reconstruct it. So in summary, about sediment in CROCO, there is an increasing effort for sediment modeling. We are a lot being interested in this. So the model, I would say you can trust it more and more. Maybe it's a bit less true now, but there was a big focus on wave-dominated environment and nearshore modeling and sediment. We got some wave weather configuration. I don't talk about this too much here. Basically, we have got a configuration where we explicitly resolve wave, and that we use basically for validation. And we have underway some work about flocculation and consolidation of sediment in the bed layers, and we plan to be able to implement interaction between sediment and biology, interaction of sediment with vegetation. So basically, what we have there is what is into the model, what is on the scheme. So we are able to transport the sediment where they are in the water column. We are able to erode the sediment. We're able to have settling of the sediment, to move the sediment through bed load, and we are able for cohesive sediment to have flocculation and deflocculation of sediment, meaning that for cohesive sediment, you will have some aggregation, disaggregation of sediment through turbulence and collision. And all of this, it's something you will be able to test in the different test cases, which in those test cases, they focused on one given process. So I think that's all about the code itself.
Thank you, Rachid. Questions? Well, it's not. And make a small break, 5 minutes, and then we will see the presentation from Guillermo on the test cases in the CROCO code, I think. So let's convene in 45, no more than 5 minutes. Thanks.